All right, and for our final talk, George is gonna, I guess we're gonna go out with a bang, because we're gonna talk about disequalities. Go ahead and laugh there, because there we go. Thanks, Phil. And this is also for use inside of Theorem Prover, so please take it away.
All right, thanks, Max. All right, so my name is George. I'm going to talk to you about disequalities in EGRAPHS, some experiments we did. And the experiment, the context of the experiment is our own inductive automated theorem prover, and it's automated, so you don't have to mess around with lean or with rock being the new name of coq. And it's inductive because it does induction. So it does this all by itself. But it's kind of domain specific, and the domain it worries about is these things: algebraic properties, commutativity, associativity, idempotency. We want to prove these things, and we want to show that some code, particular code, satisfies these properties, which are pretty essential both in code, so you get to see them in standard libraries such as Scala. So they are not checked, they are just there in documentation that please make sure whatever you give me is associative so that I work correctly. And they're also in some papers to enable some optimization. Our approach to checking these things is to lift them up to the types, so that just as I say that addition is a binary operation that takes two integers into an integer, now I also say that it's commutative and associative. So far it's just part of types. Just a quick example to show you a flavor of what Propel looks like so that I can get into disequalities is this thing. I hope you all agree 1 plus 0 is 1, which is equal to 0 plus 1. And the same goes for 2 and 3. Very easy. Now, what's really fun is that we can also talk about vectors of two numbers. So if I group these things in vectors, addition of vectors is pairwise addition. And why is this correct? Why is it still commutative? It's because zip with or pairwise has this very nice operation, which is if you give me a commutative operation, I will lift it into another commutative operation. For example, maximum. The proof still holds. Why? Because maximum enjoys this property. And inside the code, we implement it exactly like this. We say that zip with is a function. It's a higher order function. Takes a function from pairs of t's into a t that is commutative, associative, and idempotent, and produces a function over list which has the same properties. This is just a signature. The implementation is the trivial one, so we do not actually have to do any proofs. But now that things are in the type system, it means that we have to actually have a type checker that is doing the proofs, that will check that these properties hold after. So we kind of have this automated prover and the type system interplaying together. We use the type system as a kind of database for these properties, and the automated prover just looks them up, and the type system calls the automated prover to make sure the type is correct. So at the end, what we're going to do is just to search for a proof, and it's just an equational proof, because commutativity, associativity, all of these things are just equalities. So far, nothing about disequalities, but this is coming up. Here's a quick example about how Propel actually works inside. Maybe just look at the bottom, and you will see some very interesting historical abuse of notation, otherwise called operator overloading, where piano just uses plus for both addition and successor. Anyways, the Scala implementation is on top. And this is what we're going to work with. The proof we're going to do, and sure, this is all automatic, so this is going to be the very last proof you will ever see in your life, because then you can use our tool, and you won't have to do proofs. So this is the proof we're going to do. We're just going to show that adding the successor of A and B is the same as adding A and B and then doing the successor. But what Propel actually proves is not exactly this. It inlines the definition of add into this thing, but this is really cumbersome to read. I will just use a simple synonym and just use mu for this case analysis. We don't have kind of knowledge of recursion. So whenever you see add again, it doesn't know that add means this function. So it's just a symbol at this point. Anyways, what Propel really loves are these case analysis. It will just consume them and digest them. And it sees two of them, one on the left, one on the right. It starts with the one on the left, breaks it up into two cases. The case where B is 0, which means that B is not a successor. We can already see some kind of disequalities here. But there's the alternative case. And there we use kind of this trick from the type system to create an induction hypothesis, which we don't really need right now. But this got rid of one mu. So one case analysis on the left, there's still the one on the right? So it will do exactly the same thing. It will destruct on the right into 0, which was this slide, and then destruct on the right into successor, which is this case. Very importantly, we did not do rewrite. So after figuring out that B is 0, we did not replace it and then do symbolic evaluation. That's not what Propel likes to do. So we won't go through all of these proofs. We'll just focus on, I have a missing slide. We'll focus on the top left one. Just ignore the other three. And this one clearly is wrong. If it's not too obvious, it's because in the equality we have that B is equal to 0 and B is not equal to 0. So we can immediately get rid of this case and move on. That's finished. But most of these inductive theorem provers, as far as I know, do not have these disequality edges. So they are essentially stuck in this case. How would they progress? They have to eliminate this case somehow, right? This is how you would do it. You would first eliminate a constructor, then apply a lemma, apply one of the equalities that you know, another equality that you know, and finally reach reflexivity. A is always equal to A, so you kind of proved this case. So, okay, you can move on. But notice that now this step, this proof took like 5 or 6 steps as opposed to just one. This is kind of important because what we really chose really well these rewrite rules to reach the end. What in fact will happen is that we will branch out into multiple of these rules and then try all of these things, hoping to land on a really nice configuration of these rewrite rules, which is a kind of saturation, in fact. So hopefully right now you see that these equalities and disequalities are quite helpful. This equality allowed us to eliminate immediately a proof. In practice, what we did is we created this very nice picture from the proof that addition is commutative. We disabled looking at disequalities, and which is this kind of red blobs. And the green ones, which are more interesting, are the ones where we used the disequalities. And you can already see that most of our time was spent in trying to eliminate these cases where using this equality would have helped. But also crucially, using disequalities allowed us to discover kind of these clusters where my cursor is pointing, which could be interesting cases to look at. So in practice, we didn't just use it on one simple proof. We took some cases like replicated data types being a particular kind of data type that requires algebraic properties. There we saw a lot of kind of time improvement. And there was one case where we couldn't complete a proof. Divide and conquer algorithms just didn't care about disequalities, and for an inductive prover benchmarks, it was kind of the same as the first case. I hope right now you kind of believe me that disequalities are important. They helped us a lot. So how are we doing these things? Propel is kind of naive on this level right now because we just wanted to implement something and we didn't really care about this stuff up until now. So what we do to store these equalities is that we essentially use a union find without flattening. So we have a map like this on the left and it maps into a union find like that on the right. We don't even collapse paths, and that didn't seem to matter all that much at that point. So how do we do disequalities? Disequalities are a little bit more interesting. They're actually have nothing to do with union finds. And just to tell you how they look like, let's consider this case expression on the left. And if we zoom in on the very first case, where x and y are both 0, what we get is a kind of a CNF formula on the right, which says that x shouldn't be 0, so to prevent the second case. or y should not be a successor to prevent the second case, and something to prevent the third case. And at the end, we encode them as these things. So these are nothing to do with union find and EGRAPHS. But we want EGRAPHS, right? And I'm not going to preach for the choir. We all know why EGRAPHS are cool, and that's why we want them. But what EGRAPHS are not something that can help us find a contradiction, as they are right now. They can tell us when two things are equal, but not when two things are kind of not equal. So our approach was to do something very, at the beginning, was to treat equality as kind of an uninterpreted function. Just kind of embed equality within your language and then talk about it. And then we gave it some semantics, which essentially means there are some rewrite rules which we apply. Being that when two classes are equal, then we rewrite them into equality of AB equals true. And when equality of AB equals true, we rewrite it as class equality. Right? Simple example. We take some equalities, inequalities on the left, and then we rewrite them into purely equalities on the right, which is something that EGRAPHS can do. We build the EGRAPH, we get something like this. About notation, the boxes inside boxes notation, I find it confusing. I prefer this notation with circles meaning classes and boxes meaning terms. So essentially, this would be the EGRAPH for this equation on the right-hand side. We apply the saturation, and then we get this particular EGRAPH. One thing that will be relevant later, worth pointing out now, is if you look at the equalities in the true class, you'll see that they all look the same, which is an equality with two arguments that both point to the same class, which make a lot of sense. I will come back to this later. Okay, now let's introduce a contradiction. If I say 0 is not equal to 1, then x is equal to y. These two contradict through the middle rules. If I then build the EGRAPH for that and saturate it, I get the following, which is if we look at the class for true, we'll see that false is also inside it. That's a sign of a contradiction. So when you find, when you want to find a contradiction, just look whether true is equal to false. The upsides of this approach, which is embedding, is that, well, we didn't have to touch EGRAPHS. We just used them, and it all works out. The downside is that, here I'm quoting Nelson, so from the PhD thesis of EGRAPHS, essentially, is that incrementality now isn't so obvious. Now you have to saturate before you get incrementality, which might be something you are willing to sacrifice. But let me ask you this, about this thing. We did kind of a comparison, which is we took 15,000 equalities, and then we changed the ratio of equalities to disequalities. So on the left-hand side, all of them are equalities. On the right-hand side, all of them are disequalities. We looked at the ratio of nodes over classes, and then you can kind of see a degradation. So it performs worse the more disequalities there are. But something also worth pointing out is that in this ratio is that it's always less than 2. Which means on average, every E-class only has one E-node, which means it's pretty useless, right? Because the whole point of the E-class is to say equality of at least 2 things. So that's already a sign that maybe that's not really the right approach. But yeah, anyways, in real life, we looked at who actually does this, because in SMT, this is quite a common problem. You want to represent disequality. We saw that Z3 and CVC5 do this. But we also looked again, and we found that maybe we are doing this in Propel. This is from some internal slides we have at the group. And what we do is we don't quite do embedding, we do lifting. We realized that Propel was able to reason about an embedded equality up to the meta level, which is this very last 2 theorems. I won't stress too much, but this kind of made me reflect on myself and realize that maybe we are doing this thing and we should do something else. So we did something else, and we looked again at what disequality is. So disequality enjoys congruence. Pretty obvious, but it also means that disequality is not a relation between E-nodes. It's rather a relation between E-classes. And we looked a bit at this idea, and we found out that Nelson, for those who are very good observers, they might realize this is the same code as before, just expanded a bit longer. And Nelson also realized that, well, disequalities are important. And he says that if we want to check that disequalities, that two things are not equal, we have to modify the EGRAPH itself to do this through some kind of a change in structure. Alongside this paragraph, there was this very beautiful figure, and we see the structure that he did. He just introduced this extra kind of edges between classes, which are these disequality edges, meaning that what we were trying to solve was there all along. Pretty fun. So let me show you how they work. This is the same example as before, except right now we don't have these equality nodes anymore. We just simply connect the class of 0 and the class of 1 with a disequality edge. Pretty cool. Let's add the contradiction. And then we don't even have to do saturation. We just kind of rebuild the EGRAPH. And all of a sudden, you see that this particular class is not equal to itself. Obviously, contradiction. So if you have a contradiction, what do? You search for a class which is not equal to itself. And that's how you can tell. Right, that's what I just said. So how did we actually implement this? We didn't go about writing our own EGRAPH because that was why when egg exists. So we extended it. We called it diseg, and instead of showing you like pseudocode, I'll show you the steps so you can do it. First of all, you add this particular field to the E-class struct called forbid. It's just a vector of other E-classes. Forbid is a name that Nelson came up with. And if you don't use forbid in Google Scholar, you will never find anything related to disequalities in EGRAPHS. It took me forever, but it's very important to call it forbid. That's why I'm keeping this name. Then when you want to perform the union of these two classes, you just move the forbid list from one class into the other. So essentially the one being merged into. When you want to say that two things are not equal, I just called it disunion. Just add the class of one into the class of the others and vice versa. Pretty simple. When you want to check that if there is no contradiction in your EGRAPH, line 2 says go over all of the classes. Line 3 says get their IDs. Line 4 says go through all of the E-classes in the forbid list. And line 5 says check that they are not the same. That's pretty much. And if you do this, you have this egg. That's kind of the changes you have to do to egg to have disequalities. In real life, we found an SMT solver that does this called OpenSMT. It's quite a competitive and good SMT solvers if you want to use it. But now back to this question is how does it compare with this embedding? And luckily the edges, which is on the right-hand side. So on the left was the same graph which we saw a few slides earlier. On the right, in these edges, we see that there's actually no degradation at all in the number of nodes and classes. And crucially, we get that on average it's more than 2, which means classes now have 2 things inside of them. So they are asserting equality of things. They are not useless anymore, hopefully. So that's pretty good. Then we kind of did this toy setup. So now this is the setup that I based these graphs on. What I did, we generated 30,000 pairs of S expressions over 3 functions of different arities and 5 numerals, which we assert are not equal up to some depth. And then we kind of do this experiment where we change the ratio of pairs, whether they are equal or unequal. And then we were interested in the time to find the consistency, so whether there is a contradiction or not. Surprisingly, well, maybe not, the edges performed much, much worse than equality embedding. Why? Because equality embedding is about asking whether 2 terms are in the same class or not, which is pretty fast. Whereas this equality edges has to loop through all of the classes, then through all of their forbid list to find these things, which is why there's so much order of magnitude difference. But I have a little asterisk on top, and for those with good eyesight can read on the bottom is that, I will read to you, you don't have to read it. Using the naive consistency check for disequality edges. So naively looping through all of these things gets you this performance. Optimizing it, you can get rid of this and just have it like a Boolean lookup. So as you merge, you can check the consistency, store it in a Boolean, and just return that Boolean, making it even faster than the other one. But I have to show something where embedding is better. So there it is. But of course, there is a context through all this. So we asked about whether we find contradiction given a graph. But if we consider also the steps of getting to the graph, which is building the graph, then because of the saturation, we see this exponential blow up, whereas with the disequality edges, just flat. But we wanted some more realistic data. So we took the EUF benchmark from SMT-lib. So this means equalities and uninterpreted functions. And then we implemented our own SMT, like very tiny SMT solvers using Minisat, egg, and our extension disegg. We also optimized this thing I talked to you about checking whether there's a contradiction or not. And then we kind of ran it on this. We selected all of the cases where we could solve in under 1 second, which were about 1,600 files. And what you see here are these 3 numbers. These are ratios. So this would be, first of all, how many nodes there are more if you use embedding. So if you use embedding, there will be 66% more nodes than if you use disequality edges. Classes are pretty much the same for both approaches, but the time to find whether there is a solution or not is 10 times more if you use equality embedding. So the crucial question, is this a landmark contribution? Did we just make SMT solvers 10 times faster? Sadly, no, because I did not measure the time to actually do SAT solving, which is the dominant part of solving the problem, and then saturating these universally quantified axioms that you put inside of your SMT files. And I think with that, I'm done. One thing I should say is that if you are interested in our prover, Propel, we will be presenting it on Friday at 3 in the afternoon in Popuri, in this room at 3 in the afternoon. Please show up. And there's these 2 papers for you to read. It's very fun. There will be a quiz later. And with that, thank you very much. I hope the last talk was fun. Yeah.
Thank you so much. We have time for a couple questions.
Very good question. The answer is I did not actually know about E-class analysis before doing this. It was just 2 weeks ago, in fact, I learned about it. So now I actually have something to do, an experiment. Thank you.
Hi, I was just wondering how false is encoded in Propel?
How false?
Is it just like an empty inductive type, or?
We do not encode false, in fact.
I see. So when you gave the example earlier on,
So
yeah, when you got the A equals A, so you could finish it.
yeah, just give me a second. Yeah,
Could you have encoded?
No, so here the insight is that from a contradiction, B equals 0 and B is equal to successor. Well, from a contradiction, anything follows, right? So you should be able to somehow construct a kind of a reflexive term using this contradiction. So usually, yes, for example, in ROC or in Lean, false is encoded as kind of not something, and then you treat it as a function which you call with a contradiction and you get false. This is, we could do this, but well, we don't, I guess, sorry.
Okay, thank you very much.
Thank you.
And that's it for the program. Thanks, everyone.